Hello, I'm Nick Ivanov, a PhD student from Secure and Intelligent Things Lab in the Department of Computer Science and Engineering at Michigan State University. Together with my advisor, Dr. Qiben, we are delighted to present our work, System-Wide Security for Offline Payment Terminals. First, I will introduce the problem associated with offline payment terminals. Next, I will talk about our novel solution, VolgaPay. Then I will demonstrate the performance, efficiency, and scalability of VolgaPay in real-world scenarios. And then I will conclude with a few final words. Let's get started. Self-service payment terminals allow to reduce costs, increase efficiency, and extend work hours of typical point of sales. The most popular type of payment terminals is online payment terminals, in which a client shares payment credentials with the terminal, and the terminal forwards these credentials over the internet to remote services for transaction processing and approval. Typical examples of these terminals are vending machines, modern parking meters, self-service fuel stations, autonomous self-service checkouts at supermarkets, and even self-service banking systems. Unfortunately, these online solutions have been notoriously costly and hard to install in many locations. Internet connectivity requires additional hardware, wiring, and paid subscriptions. Moreover, some locations may not be physically secure, or they may not have a proper internet access available for the payment terminal. This is why online self-service payment terminals are commonly seen only in secure buildings and urban environments. To overcome these shortcomings, the systems with air-gapped offline terminals are becoming more and more popular. In these systems, the terminal communicates with the merchant servers with cryptographic tokens, using clients' mobile devices as proxies for communicating with the internet. The widespread adoption of smartphones and other handheld internet devices makes token-based payments available to most people. Since the self-service payment terminals in these systems are isolated from the cyber realm, the system exhibits a smaller attack surface and potentially less expensive to implement and deploy. This allows to solve all the previously mentioned shortcomings of online terminals. Unfortunately, offline terminals also experience some challenges. First, the transactions from all payment terminals that belong to one merchant need to be stored in a centralized database, which is also a potential single point of failure. In recent years, cyber attacks have caused massive outages of various online services and leakage of millions of online credentials. To prevent such unfortunate situations, our goal is to make sure that this database, even if compromised by an attacker, does not constitute a single point of failure or a point of mass leakage of sensitive information. Second, the user still needs to share payment credentials with the merchant over the internet. A crooked merchant might abuse those payment credentials for their own benefit. Moreover, a third-party attacker might steal the payment credentials in the process of being exchanged with the merchant. For example, credit card skimmers have been used by attackers incurring millions of dollars of damages every year. The goal of this work is to prevent the abuse of payment credentials by the merchant, as well as not letting a third-party attacker to steal these credentials. The third challenge is the establishment of trust between the user and the merchant. With the growing number of self-service terminals, as well as increased availability and reduced cost of modern technology, it becomes increasingly more difficult to verify the authenticity of a self-service terminal. Unsurprisingly, there are more and more reports of malicious, fake self-service terminals, especially in rural and remote communities. Therefore, our framework must not assume the trustworthiness of any merchant. Last but not least, while offline terminals save some money by not connecting terminals to the internet, they may require additional security protection and more expensive in-person maintenance, such as software updates, which cannot be done remotely, of course. So our goal is not to introduce unexpected costs or other inconveniences. To overcome these challenges, we design a new framework for deploying networks for offline payment terminals. This framework is based on three major insights. First, we replace open payment credentials with non-reusable, cryptographically verifiable, blockchain-based tokens. This allows to exclude the necessity of trusting the merchant by the client. Second, we introduce a hash chain-based payment channel, which allows to significantly reduce processing time and cost. Third, we use a side chaining technique called blockchain grafting for reducing otherwise unacceptable transaction costs and delays. Blockchain grafting allows to store and process transactions in a private blockchain, which does not require paying transaction fees, whereas the public blockchain is used for verification of the private blockchain and bulk clearance of multiple transactions using only a single 256-bit hash. This arrangement allows a merchant to prevent paying fees for processing every transaction, like we see in the case of credit cards or online systems like PayPal, which is a significant incentive for the merchants to start using VolgaPay in lieu of traditional payment clearance methods. Combining these insights, we designed and implemented a framework called VolgaPay for deploying secure networks for transactions with self-service terminals. VolgaPay is a transaction-based framework. The transaction starts with the user mobile device using a local channel, such as RFID or QR code or Bluetooth, to engage with the offline point of sales terminal. The terminal sends to the user some verifiable transaction parameters, such as price. Then the user sends the transaction to the merchant transaction system, which includes the public blockchain for funds management and public verification of the identity and trustworthiness of the merchant, and the private sidechain used for processing transactions and keeping intermediate balances. Since blockchain is unable to sign tokens, we use a set of dedicated token signers, which can be deployed on independent servers, or as an alternative, they can run as parallel processes on the same servers that are used as the private blockchain nodes. The signers listen for the event of an incoming transaction in the private blockchain. If the transaction is correct, which is checked by the smart contract deployed on the blockchain, the signers record their signatures in the smart contract deployed on the private blockchain. Then the user device immediately retrieves these signatures from the private blockchain and aggregates them into a single cryptographically verifiable payment token, which is subsequently verified by the offline payment terminal and exchanged for merchandise or a service. Next, let us see how VolgaPay performs in the real-world setting. For that, we have implemented a fully functional prototype of the VolgaPay system, which includes the distributed transaction system based on the Ethereum blockchain with smart contracts written in Solidity, as well as the payment terminal software written in Python. And we also created a mobile Android client app written in Java. Then using this prototype, we measured the transaction approval latency using 3 different internet connections of the mobile client. Fast Wi-Fi connection, 4G LTE, and 3G, which reveals that a typical VolgaPay transaction takes between 9 and 12 seconds, and the internet connection speed does not significantly affect the speed of the transaction. We further compared VolgaPay latency with traditional transactions. For that, we measured multiple transaction delays using credit cards with multiple parking meters, ATMs, and vending machines in different locations. And we saw that the average delay of those transactions is about 11.7 seconds, which shows that VolgaPay is on average slightly faster than traditional self-service terminals. Next, we evaluated the scalability of VolgaPay with respect to the available bandwidth of the signer blockchain channel, which is the likely performance bottleneck, especially as the transaction throughput of the system grows. Our measurement shows that VolgaPay is capable to process thousands of simultaneous transactions with reasonable available bandwidth of the signer blockchain channel. For example, a 100 megabit per second signer downlink connection is sufficient for about 5,000 simultaneous transactions in VolgaPay. Moreover, the uplink requirement is even lower. For example, the same 5,000 simultaneous transactions would require only about 20 megabit per second uplink channel. To summarize our work, we proposed the new system, VolgaPay, which is a novel blockchain-based framework for deploying networks of offline self-service terminals. We showed that VolgaPay is cost-efficient, fast, and scalable. Most importantly, VolgaPay delivers security for the entire system, not just a single terminal, such that if one participant of the network is compromised or abused, the deployment at large remains functional and safe. And we are currently working on the formal proof of security of the architecture used in VolgaPay. And we also work on the perspectives of repurposing of this design used by VolgaPay for other applications. This work has been done at Secure and Intelligent Things Lab at Michigan State University. Thank you for your attention, and I am ready to answer your questions.